Hi guys, welcome back to YouTube channel Chemistry Live UGPG. Today we are going to talk about carbonyl compounds, lecture 6. So this will be highly beneficial for BSc Chemistry students under CBCS syllabus. I have a simple message for you guys. Please think for innovation, be creative, learn everywhere, anytime, and help to learn others. So today we are going to talk about substitution reactions, active methylene compounds, keto enol tautomerism, preparation and synthetic applications of diethyl malonate and ethyl acetoacetate. So let's start with substitution reactions. So this is coming under CC6 paper unit 3 carbonyl compounds. So usually the nucleophile will attack to the carbonyl compound which contains a leaving group Lg. So when this nucleophile lone pair will attack this carbonyl carbon, C double bond O will break on oxygen. So as a result, you end up with tetrahedral intermediate. And since this is a good leaving group, so when this O minus will come back, it will kick out Lg as Lg minus. So you get this nucleophilic substitution product RCONU. But usually the carbonyl compounds like RCOH or RCOR, aldehyde or ketone, the R group or hydrogen, that is not a good leaving group. So what happens there? So nucleophile will attack to this carbonyl carbon and C double bond O will break on oxygen. So as a result, you end up with this tetrahedral intermediate. So instead of departing H as H minus or R as R minus, so oxyanion takes the proton from solvent and giving rise to nucleophilic addition product. So next is keto enol tautomerism. So tautose means same, merose means parts. So the structural isomers which differ in the relative positions of their atoms and are in dynamic equilibrium with each other are called tautomers, and the phenomena is called tautomerism. So this is the acetone that we can write in this fashion. So this CH bond will come here and C double bond O will break on oxygen. So as a result, you get this enol. So in plus OH means all, alcohol. So enol. So usually the keto form remains 99% major and enol form remains minor 1%. Similarly, this tautomerism also found in oxime and nitroso, nitro and Sc, and enamine and imine compounds. So next is active methylene compounds. So if you start with this compound CH3COH, CH3CO, CH3 acetone, CH3COO, C2H5. So with respect to this carbonyl group, this is alpha carbon. With respect to this carbonyl, this is alpha carbon. And with respect to this carbonyl, this is alpha carbon. So hydrogen atoms attached to this alpha carbon, that is called alpha hydrogens. So these alpha hydrogens with respect to this carbonyl group are acidic in nature. So the acidity of alpha hydrogen atoms is due to resonance stabilization of carbanions. So here the hydrogen can be lost, giving rise to a carbanion, and which is resonance stabilized. Similarly, when a methylene group CH2 group is flanked by two CO groups or other electron withdrawing groups like cyanide or nitro group, then the methylene hydrogens are found to be more acidic. So the carbanion so generated is resonance stabilized to a greater extent. So here with respect to this CO group, this is alpha carbon and the hydrogens will be alpha hydrogens. And with respect to this CO group, this is also alpha carbon and the hydrogens are alpha hydrogen. So since these hydrogens are flanked by two electron withdrawing groups, so this will be more acidic. So this can easily lose a proton giving rise to a carbanion. This carbanion is resonance stabilized. So C minus comes here and C double bond O will break on oxygen. So when this O minus will come back, so this double bond will migrate here and C double bond will break on oxygen. So as a result, you end up with three resonance stabilized structures. So carbanions are stabilized by resonance to a greater extent. So this CH2 is called active methylene group. Similarly here, this CH2 is flanked by carbonyl group and cyanide group. It can easily lose a proton giving rise to carbanion, and this carbanion again resonance stabilized. So such methylene group is called active methylene group, and the compounds containing such active methylene group is known as active methylene compounds. So examples are ethyl acetoacetate and ethyl malonate. These two are in your syllabus. So here you can see this CS2 is flanked by 2 electron withdrawing group CO, and then ethyl malonate, this CS2 is flanked by 2 electron withdrawing groups. So these are active methylene groups. And the compound ethyl acetoacetate and ethyl malonate are known as active methylene compounds. Next is preparation and synthetic applications of diethyl malonate. So for preparation of diethyl malonate, you have to start with potassium cyanoacetate. So you react with ethyl alcohol and HCl, you end up with ethyl malonate. Next is synthetic application. So first we can go for synthesis of mono and dicarboxylic acid. First is synthesis of N-valeric acid. So diethyl malonate, you react with sodium ethoxide. So it will take the proton from this CH2, you get CH minus carbanion, and you would react with NC3S7Br, alkali halide. So you will end up with this product, and further hydrolysis with the potassium hydroxide, you will get this potassium salt, and upon acidification, you will get this dicarboxylic acid. And upon heating, it will lose one molecule of carbon dioxide, giving rise to N-valeric acid. This is the monocarboxylic acid. Similarly, synthesis of dicarboxylic acid and beta keto acid. So we can synthesize succinic acid starting from diethyl malonate. So diethyl malonate, upon reaction with sodium ethoxide base, so it would take the proton, so you generate a carbanion, and you would react with ethyl chloroacetate. So this CH minus will attack this CH2 and it will kick out Cl as Cl minus. So you will end up with this product. So this upon hydrolysis, KOH and reaction with HCl, you will end up with this tricarboxylic acid. And upon heating, you will lose one molecule of carbon dioxide from here, giving rise to succinic acid, dicarboxylic acid. Similarly, synthesis of acetoacetic acid can be done. Diethyl malonate reaction with sodium ethoxide, you get this carbanion CH minus C2H5 twice. Then you can react with acetyl chloride, giving rise to this product upon hydrolysis with potassium hydroxide, and further reaction with HCl, giving rise to CH3CO, CH, twice. Upon heating, it will lose one molecule of carbon dioxide, giving rise to acetoacetic acid, CH3CO, CH2COH. Next is the preparation and synthetic applications of ethyl acetoacetate or acetoacetic ester, AAE. So this is the compound ethyl acetoacetate. So this can undergo keto-enol tautomerism, giving rise to the enol form. Then next is methods of preparation. So if you start with ethyl acetate, 2 equivalent, and you react with the base sodium ethoxide, you will end up with ethyl acetoacetate. So what is the mechanism? So you start with ethyl acetoacetate. So C2H5O minus will take the proton, you generate a carbanion. So this CH bond will break on this carbon. You generate this carbanion, and this carbanion is resonance stabilized. Once you generate this carbanion, it would attack another molecule of ethyl acetate. So CH2 minus will attack this carbonyl carbon, and C double bond will break on oxygen. So as a result, you end up with this oxyanion. So when this O minus will come back, it will kick out C2H5O minus. So loss of this C2H5O minus, giving rise to the products ethyl acetoacetate. Then another method of preparation of ethyl acetoacetate is dimerization of cation and further treatment with ethanol. So this is the cation, you react. So this C double bond C will attack to this oxygen, and this pi bond will attack to this carbon. So you end up with this 4-membered cyclic compound, and further reaction with ethanol. So this oxygen lone pair of ethanol will attack to this carbonyl carbon, and C double bond O will break on oxygen. So as a result, you will end up with this protonated species. Again, when this O minus will come back, this CO bond will break on oxygen. So you will end up with this enol form of ethyl acetoacetate, and which tautomerizes to give rise to ethyl acetoacetate. Then next we will move to synthetic application. So we can prepare diketone, that is acetyl acetone. So ethyl acetoacetate, upon reaction with sodium ethoxide, you generate a carbanion because this is active methylene group. So again for the reaction with the acetyl chloride. So this CH minus will attack this carbonyl carbon and it will kick out Cl as Cl minus. So you will end up with this add-up. So this product upon treatment with S3O plus and heat, it will lose one molecule of carbon dioxide and ethanol, giving rise to acetyl acetone. Similarly, we can prepare alpha beta unsaturated acid. So if you start with ethyl acetoacetate, upon reaction with pyridine, you generate a carbanion, and further reaction with acetaldehyde, you will end up with this unsaturated compound, which upon hydrolysis, it will lose one molecule of ethanol and one molecule of acetic acid, giving rise to crotonic acid. So with respect to this carboxylic acid, this carbon is alpha and this carbon is beta. So this is alpha beta unsaturated acid. Similarly, another synthetic application is synthesis of a heterocyclic compound. So this is the urea NH2CONH2 and this is the enol form of ethyl acetate. So they will undergo cyclization reaction. It will lose one molecule of water and ethanol, giving rise to 4-methyl uracil. So please subscribe to our channel Chemistry Live UGPG. So this is also available in the website chemistryliveugpg.com. For class 11th and 12th students, this is the channel Foundation Chemistry AB. So please subscribe to our channel, and this is also available in the website www.foundationchemistryab.com. So this is a simple step towards e-learning, making life better. Thank you all for learning.